I presented early findings of this study 2 years ago at the open house. And then again, last year, Omar Al-Mufti presented interpretations of the CT scans from the study. This year, there'll be 3 presentations on the results from Bilberry Creek, myself, Basan Herath, and Omar Al-Mufti. My goal for today's talk is to provide a high-level overview of several of the data sets that are coming together to characterize the Champlain Sea Aquitard. For many of these data sets, we're at the early stages of the data analysis, so I'll be presenting results with observations or preliminary interpretations rather than conclusions. The idea is to show the breadth of the investigations and some of the interesting findings that we're pursuing. So the study has 3 main objectives. First is to investigate the geological, hydrogeological, and geochemical factors that may influence geotechnical properties. Second is to interpret the geochemical changes arising from groundwater flow and diffusion, as they may also affect the geotechnical properties. And third is to establish 2 new reference sites in the Champlain Sea, because this is really an opportunity where we're using multidisciplinary geoscience to characterize a site. So this will be the focus of my talk today. So the study sites were first here, I guess on the left panel, we have the maximum extent of the Champlain Sea. And we have our study sites are in Orleans, shown on the right, BC16 and VC2. Now, these were selected by the Rideau Valley Conservation Authority and the City of Ottawa, who are leading hazard mapping studies and geotechnical investigations in these watersheds. Since the GSC had previously conducted investigations in the Kinburn and Breckenridge areas, shown here in the slide, and we'd worked on deeper sediments, we were invited to participate in 2 deep boreholes at these sites. So as you can see here by the satellite images, the arrows basically just, the satellite images show the density of the development around these creeks and watershed ravines. And then these drone pictures down below actually show what the sites look like. From down here, you can see the stream, and also the neighborhood. In terms of VC2 here, the site is right between these 2 houses behind the trees, but it gives you an idea of what the neighborhood surrounding the sites are. So the methods we used, we drilled in the fall of 2019, attempting to collect relatively undisturbed continuous core in Shelby tubes using a piston corer here or an open tube sampler. When these didn't work, we used a split spoon sampler. We installed piezometers and vibrating wire piezometers at both sites. We carefully preserved the cores on site in wax. We drove them to Quebec City and scanned them in the CT scanner. We brought them back to Ottawa, and we've been extruding them and sampling and subsampling them and running analyses on them, such in this case a fall cone analysis on the fresh sample. So in terms of the stratigraphy, we have the stratigraphy at BC16 and VC2 here, going from till at the base and then through units 1 through 4A and 4B. These were defined using the CT scans, as I'll talk about a little later. The recovery in these cores in BC16, you see the cores here, and the recovery is about 71% in 58 Shelby tubes and 11 split spoon samplers. We hit refusal at about 49 meters almost. And then in VC2, we went a little deeper. We went to 66 meters, but we didn't reach till, which is at about a depth of 80 meters. And in that case, we recovered about 74% in 90 Shelby tubes and 9 split spoon samples. A thing to note here is the fill at the top. So we basically didn't get to sample any undisturbed sampling of the weathering zone. And so let's move on. So what does the Champlain Sea Aquitard look like? Well, here we have both basically a naked eye view. So this is the photographs taken as the core, just after the core was extruded and scraped off. And then next to it are the CT scans of the same cores. And what you see is not untypical of the Champlain Sea. There's not a lot to see, really, except the most frequent descriptions are color banding, or modeling. Sometimes there's descriptions of stiffness, and if you sometimes you can see the coarser laminations, and especially if you let the core dry out, then you start seeing differences based on grain size as well. But we didn't let anything dry out, and we used often the CT scans to guide our subsampling. So now, briefly, this is reviewing a bit last year what Omar presented. These are the different units in and just below the Champlain Sea. So Unit 1 at the base, just above the till, is freshwater rhythmites. Basically, these are varves being deposited in a lake in front of the glacier, initially right at the glacier. In fact, these coarse bands are interpreted to be iceberg fallout into the proximal Champlain's, actually glacial Lacustrine Sea. Unit 2, we moved to the saline environment. So this is the start of the Champlain Sea, when the Champlain Sea invades the isostatically depressed basin. Here, along with the Champlain Sea, you get a lot of marine fauna that come in, and they start churning up the sediment, which is why you don't see the fine laminations, although you still see the overall banding. Then we move into Unit 3, where there's an increase in sedimentation rate, fewer organisms, so the laminations and the bandings remain in place, and we see diffuse parallel stratification. Now we move on up near the top of the profile towards Units 4A and 4B. Now 4A is a combination of either diffuse parallel stratification or structureless mud, and that's interstratified with some of these coarser well-developed parallel stratification. So this is Unit 4A, and interspersed with that is Unit 4B, where it's basically the same kind of sediment, but it's been deformed. So now moving on to grain size. Grain size here is I'll just present, in the interest of time, I'm just going to mostly present in the context of BC16. There's similar results for VC2, but BC16 includes the entire sediment units. So and as you can see here, the grain size profile, we have sand, silt, and clay, and basically it's mostly silt and clay. There's very little sand except in the bottom in the till and in the lowermost Unit 1. And when you look at the grain size, the ternary diagram here, you see almost all of it sits in a fairly narrow range of about 20% variation, 48 to 68% silt, very little sand. All the samples are here. Now, what's interesting though is actually looking at the samples that do have a bit of sand. There's the till at the bottom, and then there's the till immediately below the Unit 1, and then you have a Unit 1 which has almost exactly the same grain size. And when you look at these, so this is the core at the bottom, the CT scan of that core. So this is the till immediately below the start of the rhythmites, and then here is this is actually one of the iceberg fallouts. So in a sense, it's a bit of confirmation that the iceberg fallout, as you'd expect, would be kind of similar to the last till that was deposited. So that's a nice little confirmation. Now, as you move up into the varves, you see that we have here high silt, and gradually as you go higher up into the varves in Unit 1, you get more and more clay mixed in. So some of the physical properties here, we have the core in BC16. The two measurements here that are shown in the panel are water content, in this case as a percent dry mass, and specific gravity. These other two measurements of porosity and bulk density are actually calculated from this with an assumption of saturation below the water table. So the water content does, it's very high, and it does decrease gradually through the Champlain Sea deposit, and then much more rapidly in Units 1 and then through the till. The specific gravity is fairly consistent. There's a few outliers, but even there, this is not a wide range of values, so it's actually fairly constant. The porosity is what's really interesting here. We start off at extremely high values. We're almost at 70% here, and gradually decreases down to the bottom of the Champlain Sea towards 60% near the bottom of Unit 3, and then in Unit 2 drops a little bit below that, and then Unit 1 drops off very rapidly. Now, what I'll do is I've just highlighted these two samples here, and just to show that there is a wide variation within the package, just a couple of specific locations, and I'll talk about this one in the next slide. So here we have, this is our friend again, R29. This is one of these cores in Unit 4A with well stratified sand and diffuse stratification. So the grain size here in a sample just below is actually 56%, and the grain's 56% silt. And then in a similar core, although we don't have a sample in there, it's about 75 to 80% silt. So that's the main difference, about 25% difference in the silt content. As a result, you see a difference in porosity. So the porosity is lower in the well stratified sediment, about 53 versus 64% in the diffuse. Similarly, as a result, I guess you have a higher bulk density in the well stratified sediment compared to the diffuse. And that results in a change in the radio density. And so the CT scans are measuring radio density, and that's what's shown here in the red graph on the right. So this is the radio density along the length of this core. And you can see there's a great difference between the radio density for the diffuse bedding, around 1025, versus a value of about 1260 within the core sample up here. So what we also see here is that this is also plotted on scale with the downhole borehole logging of magnetic susceptibility and apparent conductivity. And we actually see that there's a close magnetic susceptibility also responds to the coarser grain sizes within the silt, which allows us both to actually make sure that we got the right, calibrate the depths of our core samples in some cases, and also to look at the relationship between magnetic susceptibility and these well stratified sediments. So here we have the correlation between this was shown by Omar last year. It's basically the correlation between the two boreholes, VC2 and BC16. So they're about 3 kilometers apart. And this is the correlations that he established based on basically the CT profiles, both the visuals and also the data itself. And so what I'm going to show here is on the right, this is actually the downhole logs logged by Heather Crow. And this is one of the downhole logs, the magnetic susceptibility. And what we see, as in the last slide, is that the magnetic susceptibility, there are anomalies along both profiles. So here's VC2, and I've plotted it at the same scale as Omar's plot here. So they're both the same depth. And this is a normal scale. We see a number of anomalies as we go down the holes. And then in BC16, what I've done is I've actually modified the scale here so that a lot of the anomalies tend to line up. So I've actually moved the scale down. It's actually at the same scale for the upper part. And then at the lower part below this dash, I've expanded the scale a bit. But when you do that, you see that the pattern of magnetic anomalies are quite a bit the same. And here's our friend R029. And basically, so that's that well stratified unit that we're seeing basically in both boreholes. And here the little dashed gray lines beneath are actually Omar's CT scan classification of the different units. So again, here's an independent source of data that's basically verifying the correlations. These are nuclear magnetic resonance results, NMR. It's a new tool that Heather Crow has just been using in borehole logging. So what we see here is basically some of the same results we've seen before: the lithology, grain size, magnetic susceptibility, apparent conductivity, and the samples, the porosity of the samples. Now, what's listed behind it here is the NMR results. And what the NMR is it's basically a strong magnetic field in a logging tool that polarizes the hydrogen atoms. So you get and then it measures the decay of that over time. And then you can kind of estimate the amount of water in different size pores. So not just the total amount of water, which is what's shown on the maximum end of these colored diagrams, but also the distribution between clay-bound water, capillary-bound water, and then basically in larger pores, so smaller to finer pores. And we see the majority is in this clay-bound water, which is not surprising because this is a mud. And then, but what we do see is that there, near the top of the hole, there's an increasing amount in these kind of middle-sized pores, which is not surprising in a sense because we're dealing with the larger pores. These are at the highest porosities within the pore, and then they gradually decrease. They tend to get smaller and smaller as we go down. The dark blue is probably related to disturbance in the annulus or surrounding the borehole. Now, there's several actual challenges in measuring NMR, especially in these kind of boreholes. Here you can see that there's a difference, especially near the bottom in both boreholes, and that also occurred in Breckenridge. And that's as the magnetic susceptibility tends to climb in the bottom of the hole. There seems to be more interference. It's also a problem to measure NMR in the tiny pore spaces because, I mean, not many sediments have, 60, 70% moisture porosity. And also there's urban background EM noise in the area. So that's things that Heather's had to contend with. We're also looking at mineral magnetism. This is Randy Enkin's work at GSC Pacific. So my understanding from what Randy tells me is that the MRS here, this is the remnant magnetization after saturation. It's a proxy of the amount of magnetic minerals in a sample. So we can see that it's gradually decreasing down near the bottom, and then it shoots off very high. We see there's a change in scale here for the upper part, so I can show it right in unit 1. And then MSP is actually the superparametric magnetization, which is a proxy for the concentration of superfine magnetic minerals. So in other words, these are the nanoscale particles that contribute to magnetism. And again, you kind of see a kind of a fairly constant pattern, going down the hole, but then a large increase again right in the bottom. And that's where we're having more of the problems with the NMR. So hopefully this will be interpreted in collaboration with the borehole geophysical data. This plot here is called a day plot, and Randy tells me basically what it's telling us is that we have either different magnetic sources or different source concentrations going from the till to the lake to the sea. So I'll move on here. This is Omar's continued his microtextural analysis of Champlain Sea muds. He's going to talk, this is part of his talk today, so I won't go into it, but you can see in optical imagery, we can see benthic organisms are actually moving sediment around. You can see it even in more detail, even at the SEM scale, and that's influencing diagenesis. Another aspect of this work is, again, following up on the CT scans, was looking at different hyperpycnal and hypopycnal flows, so different density flows. This is a picture of the actual thin section. This is the optical microscopy of the thin section showing the flocculations, and this is actually the SEM showing what a flock is. And these can be important not only just for understanding the sedimentation, but also in terms of the geotechnical properties and the physical properties of the sediments. We've been monitoring heads at both sites. So you can see here at VC2, we have basically decreasing heads as you go down in sight. So not too surprising, a downward gradient. So when you plot this as elevation versus head, we see downward head, fairly constant gradient, and it stays constant pretty well over time. A fairly high hydraulic head of 0.27 in VC2. It's smaller in VC16 at 0.03. Some of our geotechnical measurements, the fall cone measurements I showed before, that instrument I showed before. So they measure the undrained sheared strength. So they basically increase with depth, which is not surprising. And then what you do is you basically take that same sample after you've measured it once it comes out of the core, and then you remold it, you disturb it, and you analyze it again, and you get a much lower shear strength. And then the ratio of those two actually forms the sensitivity, which is kind of a measure of how sensitive the sediments are to liquefaction, or they can become quick clay. So basically, the sensitivity is just the ratio of the blue values over the red ones. And then, so basically about 1/3 of the samples have a higher sensitivity above 16. This is a bit of an arbitrary value. And in VC2, it's almost about half the samples. If you look at Atterberg limits, that's kind of the limit, the water content at which a sediment will either behave plastically or as a liquid. And then the blue dots are actually the natural water contents. So where the water contents are actually above the liquid limits, you tend to have sensitivities that tend to be high. Now, that's not the only way to define quick clay. I guess a more detailed or refined way of defining quick clay uses two criteria. It uses a sensitivity. This is the 16 value I showed on the last one is the dashed line. Well, in this case, this box uses two criteria. It uses a value of 30 and a remolded shear strength of less than half a kilopascal per, so that when you use that refined criteria, only 3 of the 59 samples, so about, I guess that's about 5% of the samples, and they occur in the depth range of 9 to 23 meters. And then in VC2, it's about 5 of 61 samples, so about 1 in 12 or about 8%. And all these, they tend to occur in either units 4A, 4B, and there's a couple in the upper parts of units 3. So then we've also measured concentrations of pore waters, so using 3 methods. So there's 2 parts here. I guess of interest. One is there's a methodological approach where we've used different methods, centrifuge, crutch and leach, and filter paper absorption, and different ways to measure these concentration profiles throughout the profile. And then, of course, there's the interpretation of these results. So these patterns are kind of what we see at other sites like Breckenridge. It's very consistent with a downward flow and diffusion to a lower freshwater boundary. The peak concentrations here are about 15% seawater. We've also looked at cation concentrations. Again, there's the methodological interest, but these are also important because cations become important for cation exchange reactions, which of course can influence the geochemical environment. And of course, we've done these are actually Magda's results at U of Ottawa here for all these concentrations. And she's also looked at exchange site chemistry. So looking at on the top scale and the circles here, those are the exchangeable cations versus plotting on the bottom scale what are mobile, so what's actually in the pore water. And basically, these multipliers are the difference in scales between the top and the bottom. And basically what it's telling you is that there's a lot more cations stored in the exchangeable sites than in the mobile sites. So
we have 1 minute left.
Okay, and I'm just wrapping up here. Next steps. So we continue the data analysis. We still have new data coming in. So we're doing micropaleontology, palynology, and the related isotopes for those. Randy will be doing thermomagnetic susceptibility. We hope to be doing measurements of hydraulic conductivity on the core, and reactive diffusion experiments are underway. Obviously, it's quite a task to integrate all these data, and then we'd like to be doing groundwater modeling of this. We have a number of publications kind of in the queue. And then, of course, there's some publications to date. These are available free online, including Omar's paper, the CT scans. Acknowledgements, especially to the City of Ottawa and the Rideau Valley Conservation Authority, who actually paid for the coring of these boreholes. And if you have any questions, you can reach me at this address. Thank you.